In this lecture, we will look at the topic of elastic collisions. Elastic collisions conserve both momentum and kinetic energy. If we are looking at one-dimensional elastic collisions, then this problem can be solved exactly. So that if you are given the initial masses and initial velocities of the two objects, you can get the final velocities of the two objects. Let's see how we solve this. We say that momentum is conserved, so P total initial is equal to P total final, which we can write as P1 initial plus P2 initial is equal to P1 final plus P2 final. And we say that the total kinetic energy is conserved, so K total initial is equal to K total final. Using 1/2 mv squared for each of the kinetic energies, we have kinetic energy of 1 initial plus kinetic energy of 2 initial is equal to kinetic energy of 1 final plus kinetic energy of 2 final. How are we to solve this problem? Well, first let's rewrite the kinetic energy equation as p squared over 2m for particle 1 initial plus p squared over 2m for particle 2 initial is equal to P1 final squared over 2m1 for particle 1 final plus P2 final squared over 2m2 for particle 2 final. So all we've done is taken the kinetic energy equation and rewritten it in terms of momenta and mass. So right now, these are the two equations that we have. This describes conservation of momentum, and this describes conservation of kinetic energy. Since this is all happening in one dimension, I haven't bothered to put the vector symbols here, but these are the one-dimensional components of the momentum. So they can still be positive, negative, or zero. These are not just the magnitudes, they're the components. So say these are all the x components. Let's rearrange these two equations. We're just moving terms around so that we have the terms related to particle 1 on the left and the terms related to particle 2 on the right. And we do this for both the momentum equation and for the kinetic energy equation. Now, however, we can look at this kinetic energy equation and realize, oh, well, if I pull out 1 over 2m1 on the left-hand side, I'll have P1 initial squared minus P1 final squared. But we know that a squared minus b squared can be written as a plus b times a minus b. And so this left-hand side becomes 1 over 2m1 times the sum of initial and final momenta times the difference between initial and final momenta. We play the same trick over here. Notice, however, the one difference. On this side, we have initial squared minus final squared. On this side, we have final squared minus initial squared. So that's the equation we have. And so this was the equation we got from momentum conservation, and this is the equation that we got from kinetic energy conservation. If we compare this with this, well, we realize that, oh, this term is equal to this term using this relation, right? Because P1 initial minus P1 final, same thing over here. P2 final minus P2 initial, same thing over here. So if this bracketed term is the same as this bracketed term, we can cancel them out. And so we are left with our momentum relationship and now a simplified version of the kinetic energy relationship. Now remembering that P is equal to mv, the momentum relationship becomes this, and after cancelling out the 1/2 and plugging in P equals mv, the kinetic energy relationship has now become this. At this point, we have two equations and two unknowns, so we can solve them and derive these two relations. This gives V1 final in terms of the masses and V1 initial and V2 initial. And this gives V2 final in terms of the masses and V1 initial and V2 initial. Now, I don't expect you to memorize these equations. Those would be supplied to you. But it is a good idea to remember how we got to them. Now, we can actually note another useful relationship. So this, of course, was from momentum conservation. This was from the kinetic energy conservation. And then the simplified version gave us this relationship. V1 initial plus V1 final is equal to V2 final plus V2 initial. This can be rearranged into this. V2 initial minus V1 initial is equal to minus, parentheses, V2 final minus V1 final. But we recognize this kind of relationship. This is just another way of writing the velocity of 2 with respect to 1. So what we find is that the relative velocity of object 2 with respect to object 1 initial is equal to the negative of the relative velocity of object 2 with respect to 1 final. This simple relative velocity equation that holds for one-dimensional elastic collisions can make solving problems quite a bit easier. However, you will need to know one of the final velocities in order to get the other final one. Let's now try and solve a problem. Read through the problem, pause the video, and try and solve it yourself. After that, we will go on with the solution. We first need to figure out how fast the ball was traveling when it collided with the block. To do this, we use energy conservation. Our initial situation is when the ball is up here, and our final situation is when the ball is just about to strike the block. Using energy conservation, we have K initial plus U initial is equal to K final plus U final. The initial kinetic energy is 0, and so is the final potential energy, assuming that we set the final height of the ball as y equals 0. So all that we're left with is the initial potential energy, mgh, and the final kinetic energy, 1/2 mv squared. Solving, we get that the final velocity of the ball is the square root of 2gh. The h here is equal to the length of the pendulum, and so we find that the speed of the ball just before it hits the block is 3.7 meters per second. We now examine the elastic collision between the ball and the block. We use the one-dimensional elastic collision equations that we just derived. We set the ball as mass 1, so that we have m1 is equal to 0.5. We set the block's mass as mass 2, which was 2.5 kilograms. We have v1 initial is the velocity of the ball just before collision, which we determined to be 3.7, and we set v2 initial, which is the velocity of the block initially, to be 0, as the block was at rest. Plugging in these numbers, we see that in the first equation, the second term disappears since v2 initial is 0. The numerator here, m1 minus m2, simplifies to negative 2, and m1 plus m2 simplifies to 3, and v1 initial is 3.7, and so we get that v1 final is equal to negative 2.47 meters per second. So in other words, the steel ball rebounds. Similarly, examining the equation for v2 final, we see that the second term disappears because v2 initial is 0, and the first term simplifies to 1/3 v1 initial, which is 1.23 meters per second. This is a simple example of applying these equations to see the result of the elastic collision. Now let us look at a few special cases. Supposing we have that m1 is equal to m2 is equal to m, and v2 initial is 0. How do these results simplify? Also, what physical situation does this correspond to? Well, the masses are equal and object 2 is initially at rest. This is like the situation of a cue ball coming in and hitting a stationary pool ball. Let's see what the result is. Well, we see that v1 final becomes 0. This term disappears because v2 initial is 0, and this term disappears because m1 minus m2 becomes 0. So the first ball that was coming in comes to a stop. The ball that came in collided with the stationary ball. The first ball became stationary, and the second one now shoots off with a final velocity, which turns out to be equal to ball 1's initial velocity. We can see that from simplifying this equation. This term disappears because v2 initial is 0, and this term simplifies to just v1 initial because the numerator is 2m and the denominator is 2m. Here we go. Let's look at another special case. This time, we again have the second mass being stationary in the beginning, but now let's say that the second mass is much more massive than the initial first mass coming in. So, m2 is equal to capital M, which is big, much bigger than m1, which is equal to little m. If you think about it, this corresponds to the situation where the little mass, little m, is coming in and striking a huge massive object, for example, like a wall. Well, what do these equations tell us? We see that v1 final, what happens to the two different terms? Well, this term can be dropped because v2 initial is 0, so that goes away. And this term, in the numerator, we have little m minus big M. But since big M is so much bigger, it dominates, and so we can approximate the numerator as just minus big M. Similarly, in the denominator, we have little m plus big M. But again, big M is so much bigger that it dominates, and so we can approximate the denominator as just big M. So this term went away, and this term simplifies to approximately negative v1 initial. What about v2 final? Again, this second term is going to disappear because we have v2 initial is 0. And this first term? Well, the numerator is 2 times little m, and the denominator is little m plus big M, where again the big M dominates, and so we can approximate that as 2 little m over big M times v1 initial. However, this term too is going to be effectively 0 if big M is many times bigger than little m. In other words, this term will shrink down close to zero as big M goes to infinity. So what is the final situation? The big massive object continues to stay at rest, approximately, and the incoming light object bounces back with almost the same speed, but in the opposite direction. And indeed, that is what we see as the ball bounces. It bounces back with very little loss in speed, but the wall doesn't move very much. Here is another special case. Here we consider two balls. One of them is very small and light. You can think of it as a ping pong ball. And the other one is much larger and more massive, like a basketball. They are initially held with a slight separation and then dropped simultaneously from a large height. Obviously, the basketball will hit the floor first, and then as it bounces up, the ping pong ball will collide with the basketball. We would like to see what happens to their velocities. So this is what they look like during the initial drop. This is before the basketball has hit the floor. First, let's examine the basketball hitting the earth or the floor. We use the equations we derived. We set m2 equal to the mass of the earth, which is of course much larger than the mass of the basketball. The earth is not moving initially, so v2 initial is equal to 0. And the basketball is moving down with some speed v, but in the negative direction. So we have v1 initial is equal to minus v. Applying the same kind of simplifications, we see that this term disappears because v2 initial is 0. And this term simplifies to negative me over me times v1 initial, which becomes minus v1 initial, which becomes positive v. The two minus signs cancel out. And v2 final, we see, is 0. This makes sense. When the basketball hits the earth doesn't move very much, and the basketball rebounds with almost the same speed. So now the basketball is moving up with the speed v as the ping pong ball moves down with the speed v. Let's see what happens when they collide. Again, using the same equations, we continue to have m1 be the mass of the basketball, but now m2 is the mass of the ping pong ball. v1 initial is plus v, since the basketball is moving up with a speed v, and v2 initial is minus v, as the ping pong ball is moving down with a speed v. Let's see what happens. Here we have m1 minus m2, which becomes mass of the basketball minus mass of the ping pong ball, which is dominated by the mass of the basketball. In the denominator, we have mass of the basketball plus mass of the ping pong ball, which again is dominated by the basketball, and so this ratio turns into roughly 1 times v1 initial. Here we have 2 times the mass of the ping pong ball divided by mass of the basketball plus mass of the ping pong ball. And this term becomes very small and negligible since the mass of the basketball is so much greater than the mass of the ping pong ball. So neglecting this term, we end up with v1f is approximately plus v. What about v2f? Here we have 2 times the mass of the basketball. Here we have mass of the basketball plus mass of the ping pong ball, which is dominated by the mass of the basketball. This ratio simplifies into approximately 2 times v1 initial. In the second term, we have mass of the ping pong minus mass of the basketball divided by mass of the basketball plus mass of the ping pong. Again, the basketball dominates, so the numerator can be approximated as negative mass of the basketball and the denominator by just mass of the basketball. So this ratio becomes -1 times v2 initial. So overall, this simplifies to 2 times v1 initial from here minus v2 initial from here. But v1 initial was plus v, so this becomes 2v. And v2 initial was minus v, so this becomes minus v, which is plus v. And so the overall result is 3v. So what has happened? When the ping pong ball hits the basketball is not affected very much. It mostly continues upward with the same velocity, moving upward with the speed of plus v. But the ping pong ball now goes from minus v, that is a speed of v heading downward, to positive 3v, which is a speed of 3v heading upward. So our situation before the collision of the balls was the ping pong ball heading down with speed v and the basketball heading up with speed v. And now after the collision, the basketball is heading up with mostly the same speed, and the ping pong ball has its speed tripled as it shoots up. This can be a pretty dramatic demonstration in real life, which is why the ping pong ball shooting off like that is sometimes referred to as a rocket ball. Let's look at this situation again, and without having to use the exact solution for the final velocities, see how we can derive them in a slightly faster way. To do this, we use that other relation that we described. That is, the relative velocity of 2 with respect to 1 initial is the negative of the relative velocity of 2 with respect to 1 final. Let's unpack that. That becomes v2 initial minus v1 initial is equal to minus parentheses v2 final minus v1 final. First, the collision of the basketball with the earth. We know that v2 initial is 0 and v1 initial is minus v, so that takes care of the left-hand side. And we can guess from experience that v2 final would be 0, that is, the earth doesn't move very much. Plugging those in, we have 0 minus negative v is equal to minus parentheses 0 minus v1 final. Solving this, we get v1 final is equal to positive v. So, having guessed that the earth doesn't have its velocity change very much, we can see that the basketball will rebound with a speed of plus v, heading upward. Now, the ping pong ball and the basketball. v2 initial is minus v, that's the initial velocity of the ping pong ball, and v1 initial is equal to plus v. Again, we can guess that during their collision, the ping pong ball does not have much of an effect on the basketball, and so v1 final, that is the final velocity of the basketball, should be still approximately plus v. Plugging these in, v2 initial becomes minus v, v1 initial is plus v, so we have minus v minus plus v. And here we have minus parentheses, v2 final is what we want to find out, and v1 final we expect to be approximately plus v. This side simplifies to minus 2v, this side simplifies to v minus v2 final, and moving things around, we get v2 final is plus 3v. So we see that these relative velocity relations here can allow us to very quickly get through the calculation, assuming we know one of the final velocities. That is, in this case, we knew the final velocity of the basketball hadn't changed very much, and similarly in the previous calculation we assumed that the final velocity of the earth hadn't changed very much. And with those bits of information, we were able to quickly derive the approximate final velocities of the other objects. That is the end of this video. I'll see you in the next.